Well, it looks like we have 22, Mehul. This is a good time to start.
Okay. Do you see my screen? I'm sharing a PDF.
Yes.
Okay, thanks. Yeah, so this, hey, I'm Mehul Sampath. Good morning, good afternoon, or good evening, wherever you are. Okay, so this is lecture 3, and in this one, compared to the first 2 lectures, it's more general, like introduction to machine learning, and also introduction to introduction to classification, introduction to neural networks, and he does a pretty deep dive into some of the matrix calculus. And so this is part 1, and so lecture 3 is neural networks and matrix calculus, and then the next lecture is backpropagation. So these 2 are related, so that's why I decided I could maybe help and try and do these 2, and I'll give you, I'll go through the lecture notes, and my plan is to go through their lecture notes and also share some of the things I found useful while reading about these things, and hopefully some of these tools I will share are useful for you too. Okay. So the outline we talk about classification, a review or introduction to classification, neural networks, and then a side, sort of a side note, talk briefly about named entity recognition, and where I struggled a little bit was this matrix calculus introduction, but hopefully we can get through all of it. And like Joseph said last time, Joseph was showing this this graph. Like this is the response from the students. The material is pretty hard, and but it's worth it. Yeah. Okay, so for the general classification setup, right? So that's the first item for us. So generally we have a training data set consisting of samples where XI are your inputs, and you have these are labeled data sets. So you have the labels YI, which can be one of many classes, right? So in this case, the classes could be what's the sentiment of the document, right, or so on. But you could easily think of this is a more general formulation, right? So for example, let's say you had some medical data. Your XI could be the height, weight, and let's say cholesterol levels of a patient, and YI could be some classification. You could easily have this setup it works for many domains, right? So XI could be, say you're classifying flowers, right? So XI could be properties of the flowers, like say number of petals, length of size of the petals, and so on. And then YI would be the class. Okay, so this is a very general formulation, and maybe the key part here is that the XI's, the input has some dimension D, right? So if you just have X1 and X2, you are in 2 dimensions, and it's easy to visualize things, but you could think of it as like a n-dimensional space, So sometimes I think of it as I have this little cube, right? So I have this 3-dimensional space, right? And basically all your each training data set is a point in this 3-dimensional space. Okay? And as you you can think of it as also, and as you have more and more features, you say you have n features, so you are in this n-dimensional space, right? Which is hard to visualize, but basically each input is a point in your n-dimensional space. Okay, I think this figure is key, right? Like, so this intuition, like what are we doing in classification, right? So you have training data, you have the inputs, and you have label data. So here green and red, right? And okay, so the simplest case, you have this 2-dimensional feature space, right? And you're trying to draw these boundaries, right? So given your training data, you try and draw this boundary, and let's say then you let's say you have your training data, then when your test data comes, you see which side of the boundary it falls on, right? And then you can classify it accordingly, right? Okay, so here I'm going to, okay, so this idea of having the feature space and boundaries. So let me show you one thing that I like quite a bit. So this is and it relates exactly to that figure. This is the scikit-learn classifier comparison. Okay, so what they are showing here is the first column is input data of so you have two classes, say red and blue, and what we are doing here, showing. Wait, let me see if I can make this bigger. Okay, it doesn't. Okay, so each column is one type of classifier. Okay, so the first column is nearest neighbors. Then you have linear SVMs, decision trees, where you have these nice straight cuts and kind of easy to understand, right? Random forests, neural networks, and so on. And I guess, yeah, I don't want to go in, of course, this is not the place to go into the details of each of that. That will be Joseph's hands-on machine learning, which starts in a week, right? Probably we cover more of the methods there. But you see the idea is the same, right? You're drawing these boundaries in this feature space, and each classifier is giving you different different boundaries. So one nice thing about when you have scikit-learn and stuff is, I was wondering, like, okay, I want to run this code, but I don't want to install everything on my own. And I mean, I could, but I'm just lazy. Okay, so what a lot of these things have started doing is when you have a script like this, right? When you can simply just many of them have a launch in Binder. Okay, let's see. Hopefully, this live demo works. Yeah, so you can basically. And I have a couple of examples where we can launch the script in Binder and then just run it. So in this case, yeah, this is your IPython notebook, and okay, let's see. Shift enter. Yeah, that's running. Okay, that's good. Oops, sorry. Yeah, it's executing now. And what this does is it launches the instance, I don't know. Yeah, on a website called MyBinder, and it's running the code for you, and you can play with it, and you can and try it out. It's a little bit slow, but it should be maybe just a minute more.
While we are waiting, I also pasted the link on the chat. It's a TensorFlow playground. You get to see the decision boundaries in different layers for different units and play around with it.
Right. Yeah, that was. Thank you very much. Yeah, you read my mind. That's one of my links that I plan to show. That's great. Yeah. Okay. Yeah. So now, yeah, basically, see now. Okay, this worked. So you could, you can run your script in Binder and just play with these toys examples to get a feel for the boundaries. Right. Okay. Let me go back to the lecture material. So here, basically in 2D we have a line, and in 3D you have a plane, right? And I don't, so in 4D and higher Ds, I guess they're just calling it hyperplanes. Yeah. Okay. So how do we go about getting these boundaries? For each X, we want to predict what's the probability that it belongs to a particular class Y, right? And so the way we can do this is by these two steps. Is for if your classes are C, small c1 to this c, and then you can compute an f of y, right, just by matrix multiplication, like shown here, and then apply basically use the softmax function and get a normalized probability, right? So what's the probability that given an input vector, what's the probability that it belongs to a particular class, right? So p of y given x.
Hello, this is Shubhashish here. Just a question.
Yeah. Okay.
Sorry to interrupt in the middle. So the question is, this kind of mathematical stuff that they're showing, I went through this material, but these mathematics are becoming a bit difficult to understand. So any background material or something that we can go through to understand this mathematics in a bit better way?
Yeah, sure. So last week we there is Joseph led a discussion on matrix calculus, and there was this really nice document. So I would recommend going through that, and there is a channel for matrix calculus, so that should really help you. Yeah. And
so where can I find this documentation? This PDF?
It's right here in the there's a matrix calculus, and it should be here.
Okay.
Yep. Yeah, and it's yeah. Okay. Yeah. So he talks about in traditional machine learning you could minimize the so we want to maximize the probability for each class, right, given your for each training example, right? So you could minimize this, but he gives a reason for why this is not used. Sorry, I forgot that. And
yeah, that's a really good point. Can anyone provide an explanation for this? Because this negative log probability comes up a fair bit in PyTorch. Does anyone have a view of that?
So the negative log, this thing is arising because they are using the log likelihood model. In the likelihood model, you see there's a function called likelihood of theta, where you calculate the product of all these probabilities and try to maximize it. Now the problem with that formula is that it goes for the product of many very small numbers, and your calculator or computer may not be able to keep up with those numbers. So it's more convenient to convert that log equation into a log equation, and then instead of multiplying all the probabilities, you add up the probabilities. Now the problem is that because probabilities are between 0 and 1, all those numbers are negative. So to convert those negative numbers, you use minus log instead of just log.
Okay, but if your numbers are really small, surely if you do a log on them, it makes it even worse, doesn't it?
No, not at all. It's just the opposite. Like look at 10 to the minus 3, 10 to the minus 50. The log of 10 to the minus 50 is minus 50. So that's not small at all, right? 10 to the minus 50 is a number that's so small that your computer wouldn't be able to handle it. But if you take the logarithm, that puts it in the realm of small number of small integers, right?
Yeah.
You okay with that, John?
I am, yes, thank you.
Good. Okay.
Yeah. So all you need to do is just look up the likelihood formula and study that.
And not to mention, differentiation of some terms is easier than the ratio.
yeah. Okay. So in this case, he says we will try and use this cross entropy, right, for this training. So it's something that comes from information theory. Let's say you have two vectors. Your true probability is p, and you have the computed probability is q, right? And the q was just from what we saw before in the previous slide, right? So in this case, because we are doing classification, right, what happens is p becomes a one hot encoded vector, right? So say I'm classifying fruits, right? Orange, apple, banana, and I have an orange, and so I only have 0, 1, 0, right? So this equation becomes, so I'm only left with one term, which is 1, 1 into whatever the computation for Q is for that. Okay. So now, yeah, so that was for, that's for one training sample, right? So you have, you measure the cross entropy for one training sample, but then you want to do it for, you want to compute it for across your full training data set, right? So you have, you take an average across all the n samples, and this is basically just this equation. Yeah, for one object, you just, for one training sample, you have one term, right? And then for n training samples, you end up with you end up with this. So any questions so far about this?
Yes, can you explain how this formula comes from the previous page? You were explaining like the, for each entity, it is just getting summed up. So how does this?
Okay,
Yes.
so for each, okay, so we have 10 sorry, we have n training samples, right? So for each training sample, you know, like P of C, because we have the label for each training sample, right? So P of C, there is a it will be 1 for the particular class, right? And only for so only for then for you're computing the softmax only for that particular class. So P of y given x, right? So this is your Q. Okay, so in the next slide, this term is the Q, right? Oh, sorry, this term, it's basically the yeah, it's the negative log likelihood. So it's, you have this will be your Q value, right? Where is it? Okay, there we go.
So it is just a summation between, in the previous case where it was just a multiplication between the two. It is taking a summation over all the samples or all the data
Right.
points that is there.
Right, exactly. Yeah, it's just a summation, and then you take the average value of that.
Average.
Yeah.
Oh,
okay. Right. So now you yeah. So now he's writing this in matrix notation, and now basically, if you want to update this decision boundary, so as you go along the steps, as you keep you know, so you basically have you can update the decision boundaries using the derivative of this average cross entropy, which is shown here.
Just a quick question there. So we've got, so D in this case is 2, right? And in that green, and you know, the diagram that you're showing, we've got 2 dimensions here. So what exactly does the what exactly are we does that bit there actually mean? So we're trying to update the decision boundary. Okay, so why would we show that in this way?
Okay.
Right, because they at the bottom, the bottom formula is, you know, the gradient W1 and the gradient W2, as far as I understand it. So I don't know how that captures your decision boundary. Perhaps it's not relevant. Perhaps it's not important. But if you have an understanding that would be helpful.
I think each point on this visualization represents more than 2 dimensions. That this is just a representation. So for theta there we've W1 up to WD.
That's not quite accurate.
Okay.
So you have n-dimensional input and 2-dimensional output. In between, you can have anything. So these are logistic regression, if you will, like 2 logistic regressions sitting and generating an output. And W's are representing the weights to those output units from the input. And you put them into a matrix. So if the D is representing number of outputs, W's are the vectors that representing weights from inputs to those outputs individually. So they are the model's parameters, and we want to find the optimal parameter that draws the best decision boundary in this 2-dimensional problem. So the green points represent one class, and the purple points representing the other class. I guess maybe there is only one output. I was misspoken because you have one line that splits them both. So then you do the derivative, the differentiation based on those weights to such that the cost function equates to 0, and that would be your optimal weights. I don't know if I confused you more or was able to explain something there.
So just one question. So these W's, this theta is a vector of W, right? W1 to W2, that's a d-dimensional vector. Now these W's are integers or they're like individual data points, or again W's are vector again?
Yeah, I think that's what I think at least, is that each point is a vector of length D.
Right. Yep.
You mean W1 is again a vector, right? So what does that vector correspond to? This d-dimensional vector, I think this is for one data point which is having d-dimensional input corresponding to d weights are there. Now if again W1, W2 itself are vector, what they correspond to? Like why they are vectors?
Well, I think like Murat was saying, your W's correspond to basically your weight that you're multiplying by your X's, which are in this case is 2-dimensional, but it can be multidimensional, of course. So, and what you're trying to minimize is the gradient of your J theta, so that I mean, whatever in this linear function is your cost distance is the distance between each class to your boundary.
So first we have to understand what the C and what the D are. So let's make that clear. C is the number of classes in the problem, which in this case is 2. That's the capital C. And D is the number of features in the problem, which can be any number of features. So in this case, again, the number of features in this plot is 2. You know, along the X direction and along the Y direction, and the classes are indicated by green and red. Now, what is theta? Theta is is a column vector that consists of all of the elements of the weight matrices, and the notation is that capital W with the dot. Notice there's a little dot before 1. That means that dot replaces all the C's, all the classes. So if in a problem with 2 classes, W dot 1 would be a vector of length 2. Pardon? And so what you can think of is that the W's are being stacked vertically, and W dot 1 is a vector of length 2, and W dot D is also a vector of length 2. In this case, each of these vectors is a vector of length 2 because C in this problem, capital C, is 2. So when you finish stacking Pardon?
So basically, say it's a binary. Say it's a 5-class classification problem. So just building upon your illustration, if it is a 5-class classification problem, then C is 5, and say there are 10 features. So D is 10. So in
That's
that
right.
case,
And so
theta
R,
vector,
the dimension of R is C times D, the number of classes times the number of features. So
correct.
in this case, that like you're saying 5, if there were 5 classes and 10 features, then C times D would be 50, and this
Correct.
vector theta would be of length 50.
Exactly.
And what they're showing you, so this is a way to this is a way to show you, before they introduce the concept of a Jacobian, they're introducing how to do it element by element. You're just stacking all the parameters in a column vector, and then all the gradients, all the derivatives are also in a column vector.
And I think that potential confusion might have to do with the plot is showing only one line, only one of 2 outputs decision boundary, because D is equal to 2 in 2-dimensional problem.
Right.
But we are only plotting on one of those outputs.
Right. We're plotting. We're plotting in this problem. This is a special case where D equals 2. That's the vertical and horizontal directions, and C also equals 2. There's just either a red class or a green class. So this is just us visualizing in the simplest possible application of this general formula.
So if your dimensions, as you said, Joseph, is 2, which is your D, why is it that W.1 also has two values?
Because the dot takes the place of C. So
okay.
So
for each of your classes, you also have the weight associated for your feature.
Yes.
Okay.
Can you normally, so in this case, you have the 2 dimensions. So D is 2. So like your plane is D minus 1 dimension. So in this case, you have a line in this 2-dimensional space which can separate the classes, right? So if your D was 3, you have then you have a plane which is 2 dimensions. Okay, so that's the way you can.
Hi, I'm sorry, I have a question.
Yeah.
Like, isn't weight always the scalar? Like, it never depends on the number of classes you have, right? Like, usually we have the same neural network, and the only thing that changes is the last layer, which has number of nodes equal to number of classes. Like, isn't weight always a scalar? I'm not understanding how it becomes a 2-dimensional vector.
For each connection from an input to a neural network unit, you have one scalar weight.
Right.
Because you have multiple connections, so there are 2 outputs or C outputs and D inputs. Therefore, you have C times D connections, and therefore C times D scalars, if you will. That makes the full matrix theta.
Oh, okay. So So we just assume one input layer and one output layer, right?
In this case, yes. It could be later on. It could be a hidden layer, and then the more hidden layers you have, then for each layer we can think of one matrix, cascading.
Okay, I got it. So it's either a single column vector of size C into D, or you can think of it as a C times D matrix, right?
Yeah.
Yeah, thanks. I got it. Yeah.
One clarification, I think it's C into D plus 1, because as we see in the first row, the row is all ones, and then we have the D dimensions, D features.
That's only if you have a bias. The one comes from the bias. In this case,
Yeah.
That's right.
The one is the bias.
You can pull it as an input. Yeah.
Okay.
Sorry, just one much simpler question. In the we've got theta, so the top equation. What's the reason why we have W.1 and W.D? Why?
The reason is that they're arranging it. They're arranging all. Okay, normally, as someone just before me explained, the weight matrix is the weights are actually organized or normally organized into a matrix. But for this purposes of this discussion, they're they're organizing the weights matrix into a column vector. So basically in computer ease, you'd think of it as reshaping the matrix into reshaping a 2D matrix into a 1D column vector. So the little dot takes the place of the rows, right? And so so basically that's it. If it's a 50, if C is 5 and D is 10, then it's a 5 by 10 matrix, the weight matrix. But now we're reshaping it into a 5 times 10, a 50-dimensional column vector.
It's been flattened then. Is that essentially what's happening?
Pardon?
It's
Flattened it. That's exactly right. We're flattening it. Yes.
Okay. I'll move on here. Expect the spins. Okay. Okay. So so far we so why do we need neural networks, right? When we have so many other classifiers. So he explains, like, a lot of the other classifiers like softmax or say a decision tree, you have these linear decision boundaries, and even though you are in a higher space, you might have like a plane or a hyperplane. With the other classifiers, you cannot get with other classifiers you get these linear decision boundaries, right? So it would be nice to have the option to have a nonlinear decision boundary, right? So so this is the classic example, right? So you want to be able to have a nonlinear decision boundary like this, like you can chop off a piece of the feature space here and in this upper and in the upper right corner. Okay, so
I have one doubt here. So, Mehul, you just a little bit ago showed one in the scikit-learn website. There is a classification boundary. So those were containing different standard machine learning classifiers, but they were having non-linear boundaries only, right? Like the decision tree and all.
Yeah, let me. So some of those are like, even I think they even for higher order like you have these groups here like this, right? You break up a green here, a green segment here, and an unconnected green segment here. Mm-hmm. So with those other ones, it's not possible to have a split like that, even though you might have like a curved boundary, right?
I think
anyone
maybe,
else? Yeah, go ahead.
I think it might be fair to say that the other classifiers pull this off in different ways. So if we are talking about so it's like decision trees, etc., they cut the space into smaller chunks and achieve the nonlinearity that way. They are naturally nonlinear. If we are talking about like a linear regression or linear classifiers, then you put x squared, for instance, as an input to create introduce some nonlinearity, therefore obtain these curvy decision boundaries. Another point that he was raising at this point, or maybe a little later, that you can have deep neural networks, but if you don't put any nonlinearity, it's superposed to a single linear model, and you will end up always a single line or hyperplane in your this as a decision boundary. Therefore, you need to introduce the nonlinear functions like the sigmoid or the ReLU.
So basically, it is not that we cannot totally have nonlinearity using traditional machine learning models as well, but the thing is that the level of granularity or level of nonlinearity we're looking forward, that can only be achieved using neural network.
That's right. So for instance, one of the famous logistic regression, one of the simplest cases, that you're not going to get a curved decision boundary unless you introduce an input that takes a square of something or sine of something.
I think Murad has made a really good summary, and that is there are several ways to introduce, in order to get these curved boundaries, you have to introduce nonlinearities. And what we mean by that is something different than just a matrix multiplication. Matrix multiplication, like we can only get a linear boundary, and what Murad was saying is that no matter, even if you use deep networks, if you a deep network of many layers, as long as you only use linear layers, it's just equivalent to a single matrix multiplication. So you have to introduce a nonlinearity some way. And Murat summarized all the different ways you can introduce nonlinearities. One is the tree, by decision trees, you basically make a piecewise nonlinearity. The other way is to introduce nonlinear dependence into features, like instead of depending on x and y, instead of doing a linear regression on x and y, you can do a linear regression on x squared and y squared. That introduces a nonlinearity. And then the third way is the activation functions like the ReLU or the sigmoid or the tench. These are all ways of introducing nonlinearities. And when you make a deep neural network, as long as each layer is followed by a ReLU or some kind of a nonlinear activation function, then the nonlinear network then the neural network can learn a highly complex nonlinear function.
Right.
And there's no limit to how complex the function can be. It can fit any function generally with enough layers and enough neurons.
Right.
Mehul, do you mind just going back a couple of slides? I've got two questions on two separate slides. So okay, on that one, right? So so there's no good reason why for that second diagram on the bottom left corner that you'd have a pink there, right? Because you haven't got a pink dot as part of any of your inputs. Yeah. So that's just, I mean, whatever that algorithm happens to come up with something like that, but there's no good reason for that pink bit being there.
That's overfitting. That's just overfitting the model.
Yeah.
Well, I don't know if I'd even call it overfitting because there isn't a pink thing there, right?
So there is no decision to be made because there is no learning sample there. So it's an artifact. It still pulls off the same performance whether that pink is there or not. But if it turns out that, in the test set, if you have a point there, for instance, then you would register that as an error.
Fine. Yeah. Okay. And then the next slide, please, Mehul. Right. Okay. So this one, what I didn't understand is, so I appreciate why you change the values of W as you learn stuff, but why are we also changing the values of X? Because my understanding is we're changing both W and X.
This is for embedding. This is the problem where you subsume you actually combine the solving for the embeddings with solving for the weights in the neural network. You basically just add them in as more weights to be determined. So what he's showing is the previous vector that we stacked, the previous vertical vector for the weights, but now we include another vector that's stacked below it, that's also vertically stacked, and that's for all the word embeddings that we want to learn.
Yes, so like Joseph said, before it was R, the space was RCD, right? And now you also have a plus given plus V times D, right? So I guess it's V, capital V is the number is your vocabulary.
Yes.
Right. So my question is,
way to understand it is derivative with respect to W and the derivative with respect to X, because you have WX. And as Joseph just explained earlier, you were just thinking of X as whatever string, but if you have X as an embedding and you want to learn that as well as you go through the process, then your matrix would need to have two derivatives stacked. The first part, all the way from W.1 to W.D, is the derivative with respect to W, which are the weights. And the second set is the derivative with respect to, or the gradient with respect to X, and that's delta X hardware to zebra.
That is right. So basically this one, what I understand, this one is not only for the previous things, but only for checking the derivatives of the weights. But here they're checking the weights as well as the word vector. So the feature itself, they're also changing and they're learning that one as well, apart from the W.
So for example, X zebra, right, is a point in so let's say it was a 3D space, is a point in the 3D space that we're adding to this column.
That's correct. So if you understand X zebra as a word vector for zebra, so in that case, whatever dimension it is, if it is 3 dimension, 5 dimension, it is that very point. Similarly,
Right. So
for the,
why would I be taking the derivative? So I've got a point, right? So I've got x aardvark all the way to zebra. All of these are points. Why would I be taking the gradient of that?
Because you
because we
want to
want,
find out the best representation of those points in d dimensions. So you're mapping words into a d-dimensional. You're mapping each word from characters, from a set of characters into a d-dimensional embedding vector. And that d-dimensional vector is, you need to find out what it is for each word. And so you start out, like all these problems, you start out with some random, you populate it with a random value, and then you twiddle it until you get a value that gives you the best solution for whatever problem you're trying, whatever classification, in this case, problem you're trying to solve. So
Okay.
it's a way of instead of solving for embedding vectors directly, instead of solving for word embeddings directly, like we saw that the glove method does, now you're solving for the word embeddings in the context of a classification problem, and sometimes that gives you better results.
Yeah, I thought it was actually sort of like transfer learning, in which you don't start off with random word vectors. You start off, if you've like read the thing about intrinsic and extrinsic training, so you've used like an intrinsic method to come up with some representation for the word, which is sort of your transfer learning. And then in this case here, now you're trying to use a classifier on it. So you take those sort of partially trained word vectors, and now you're trying to train them a bit more to move them into your specific classification problem.
Yes, that's excellent. Yeah, that's right.
Right, okay, thank you.
Yep. Okay, so then they, okay, maybe I'll just quickly. So they talk about some relation to a neural network. I don't like that very much, but okay, yeah. With a biological neural network, so you have something called like basically neurons and axons. We can. Yeah, so we can compare like artificial neuron to a cell from the neural network. So you have the cell body, which is where your central computation is done, and synapses are where say where you have an axon from one neuron. So that's the axon, and where it connects to another neuron. So that's the synapse, where the messages are passed between one neuron to the other. So. But I don't like the biological, like too much. Like it's, like I think even Jeremy has something like that, right? Like yeah, let's just focus on the technical part. And yeah, we have. So you have the different inputs. So in the beginning, it's like from different neurons, X0, X1, X2, and then the different weights, right? W0, W1, W2, and you have the summation in the cell body, and you have some activation function, like Joseph or someone else was saying, is you need this nonlinearity, right? So and we will see some more about this, that without this you cannot really learn much. So this is okay. I'm just behind. Yeah. So there you have basically you can represent this in this matrix notation. So you have the weights vector, and you have some some bias, right? Okay.
Sorry. Another. It's been a while since I looked at this. So sigmoid is the same as logistic regression. Is that a fair statement?
Yes.
Sigmoid is used in logistic regression, but in general, it's just a function that maps another function so if you have a function that has a range that goes from -infinity to infinity, a sigmoid is a function that will map that function, squish it into a range between 0 and 1. So that's how you should think of a sigmoid, as a black box that squishes, that maps a function into a squished range of 0 and 1.
Okay, and then how does that compare to logistic regression then?
Well, that is used, sigmoid is used to implement logistic regression to get the probabilities out.
Okay, and then the link between Sigmoid and softmax. Sorry, do I mean softmax? Yeah, I think I do. Yeah.
There are multiple sigmoids put side by side and representing each output. If you have one layer, and he was pointing out in the lecture that only difference from multi-class sort of logistic is that in a logistic regression problem, you tend to drop one because of the degrees of freedom. You know, one, if you have 4 classes, identifying 3 would be enough to identify 4, you know, having 3 outputs. But in these problems, they keep all 4 outputs because of the one hot encoded representation. So each 4 output, you would have a sigmoid.
So for each of your classes, you have weights associated for that class, weight for your features.
You should think of the sigmoid as a function that can help you to calculate probabilities, because it maps things into a range of 0 to 1, and that is the range of a probability. So, for the output for a logistic regression has to be a probability between 0 and 1, and that's where the sigmoid gets used. In a multi-class problem, you can have a probability for each of the output classes.
Another interesting thing about the sigmoid is that the original theory, as far as I recall, for universal approximator, as neural networks as universal approximator, as long as they are more than 2 layers, the original theory was just a step function. However, in the learning, you cannot really take the derivative of a step function, therefore follow the gradient. And so the compromise was to come up with a similar type of behavior, but a continuous function that you can take the derivatives of, and they yield nice. Their derivation is also behaves nicely. So the sigmoid or tangent hyperbolic, which goes between -1 and +1, are the 2 that traditionally used.
Yeah, and that's because you need to differentiate. You need to have a differentiable function in order to be able to do back propagation. So that's an excellent point. They replaced the step function with a softer step function. You can think of the sigmoid as just the sigmoid or the tanh as a softer version of the step function, but it's differentiable, and therefore you can implement back propagation.
How do they deal with the ReLU functions then?
The ReLU is also, well, the ReLU, you can deal with it even though it's on the face of it not differentiable, but you can just replace the value at the derivative at 0 with 0 and then treat it as a differentiable function otherwise.
And John, just a quick note about the sigmoid. So this graph really, you know, like if you just want to get a quick familiar. So when x is infinity, you know, this the value f of when z is infinity, the f of z is 1, right? When z is minus infinity, it's 0, and when z is 0, you get when z is 0, it's 1/2, so you get a half, right? So this graph is really helpful to if you just want to.
Just because you mentioned that, I also remember that there is also at the start of the learning, people tend to pick low values for weights, so that you are on this the linear portion of the sigmoid and not too far into the sides, because you can quickly go into saturation and the derivatives become very small and you get stuck there. So starting with the small numbers, you're in the dynamic range and hopefully quickly learning and then settling down to where the weights need to be.
Okay.
The small number the small number you're referring to, that is the small value for the parameters, right?
That's the learning rate.
Weights, yes.
Small value for learning rate or the parameter value?
For the parameters.
For the parameter value.
Right. So now you can build on this basic binary logistic regression unit, right, and build towards towards a neural network, right? So you have your input layer, and you could have multiple hidden layers, right? And this is what it's yeah. So this is just with so this is a 3-layer. I think they always call initially it confused me, like, why is this a 3-layer network? You know, this is just like 2 layers, but they always call the input layer is also counted as a layer. So you have a 3-layer neural network, and do I want to say anything else here?
So I've got another question for you,
Yeah.
Mel. So in computer vision, right, the X1,
Yeah.
X2, and all correspond to your pixels of your image.
Right.
What should they correspond to in NLP?
Anyone?
Yeah, and the most general, and the most naive way to do it is to take the X's are the one-hot encoded word vectors, you know, in the vocabulary space, right? So if you have a 20,000 dimension vocabulary space, then W1 is, you know, the one-hot encoded vector for aardvark, you know, and so on. But in a more sophisticated solving of this problem, the X's would be the embedded vectors, the embedding vectors that you've already solved for elsewhere. For example, with glove or word2vec.
So Joseph, will it always be, say X1, X2, say X1, this will always be a word vector, or even X1 can be a whole sentence? Say there are 10 sentences, each sentence I consider as a feature. Is that a possibility?
Yeah, I think people have done this with sentences and with character level embedding and so on.
Right.
Yeah, but right now we're looking at, in the course, we're looking at word level or subword level
right.
embeddings.
So you're saying X1 corresponds to a word vector, because that makes sense. I don't think I understood your bit about it being an embed. So X1, so for example, in 3-dimensional space or whatever space, that is where that word is represented. Is that what you're saying?
Yeah, in some high dimensional space, like 300 dimensional space is the one they use for normal NLP modeling. Yeah, so that's what you should think of. The X's are the embedding vectors for the words.
So for example, does that mean that X1, for example, is zebra, right? But in 300 in 300 dimensional space.
Correct.
Okay.
Yeah.
Thank you.
Yes, so here he's you could have you know, like you can play with you can have multiple layers to get more to learn more complex functions, and I will show you a example with by running it in the browser. Just one second, let me see.
Sorry, Mehul, one more question. So you could go back 2 slides, right? No, sorry, yeah, that one. So am I just missing this, or why do we have that, you know, in layer 2? Why do we have that extra circle at the bottom, which is not fully connected to your X1s? Is that just
that represents the bias term?
Mm-hmm.
Okay, fine. Okay, thank you.
So okay, let's quickly look at this. So this is okay. So you know what we were just seeing is differently. You know, you have inputs, and then here I just have two hidden layers, right? And we reset this. And so in this neural network, we have, so the parameters are listed here. Let's just go to Sigmoid. So what we can do here is you start with this input data, and you can see with the Sigmoid and with this data set, it's having a really hard time. So my test loss and my training loss is pretty bad. Let's see if I okay, here it's able to quickly come to a decision boundary, and probably I don't even so this is a simpler case, so I can just do with just with 2 hidden layers, and I can come up to a decision boundary. right? So let's now, in this case, the input data was pretty easy, right? So let's look at a little more complicated data set, maybe this one. And for this, I mean, we see that there are decision boundaries here, right? But this simple two-layer neural network is not able to find the decision boundaries for this case. Okay. Huh, interesting.
I think it might be able to, if you wait a little bit. Sigmoid generally tunes very slowly.
I change slowly. Okay. I should. Okay, that's what I was wondering. Didn't think of.
Around 1,000 or so.
Oh, that's interesting that that the different activation functions have.
Or not, I guess.
Well, the test loss and the training loss is remaining the same.
Yeah.
It's not working.
Interesting.
There you go.
Yeah. So yeah, and then so the things I changed is I changed the activation function here. But now see, with these different hidden layers, you could learn these decision boundaries with more difficult data set. So I think the most difficult one here is this one.
Spiral.
And yeah, this spiral, and this one. I've had a hard time finding the right combination to, like get the decision boundaries for this. But you can play with this. I think someone else, Murat, also mentioned this. So
yeah,
yeah.
And if you add more inputs, like the exotic inputs like x square,
yeah, you can
interaction
add,
terms, it helps quite a bit.
Okay. So one of the, I wish there was a way to have no activation to show, then, so without this activation function.
The linear should be
well,
no
then you just have,
activation.
or just do an identity, right? An identity would be a no activation.
Yeah.
But there
doesn't
isn't
have
one.
that. Linear is fine. Linear is fine.
Yeah, that's the one. So you're.
Yeah, and you.
And can you add x1 times x2 as well? In that case, I think it'll learn with the linear. Because we introduced inputs that added that nonlinearity. So if you remove the squares and the interaction terms, if you will, just x1 and x2, you're only going to get a line in your decision boundary. So you still have the multiplication.
Yeah, Murat is saying if you remove the x1, x2, you won't get the fit.
Right, yeah.
Yeah.
One question here. The input we can see here, it's x1, x2, and whatever these 6, 7 inputs are there. Are we limited to? Is this thing limited to only these inputs, or we can add our own? Say, if I want to do x1 cube, can I do that?
No, this is just a demo. So this is just
the demo. Yes, but I think it's the code is available in GitLab, GitHub, so you might be able to play with it.
So is it a replacement, or should I say I shouldn't say replacement? Is it a parallel thing to AutoML? The way we try to find out.
No, don't think. Yeah, this is just to show the concept of a neural network, right? You can.
So it is not that extensive.
Yeah. This is just a tutorial, which I thought was quite nice.
Okay.
You can make, if you make the learning, you can state things what happened, like if you make the learning rate really high, like it will. You can play with that. You can see the effect of different parameters. You can add regularization. You can add different parameters to. It just helps a lot to.
Just to understand the thing visually, so that we can get the feel.
Yeah. I'm sorry, I'm just falling a little bit. So here he's describing how we have. This is the matrix notation for a single layer. So you have the weight W11 times x1, W12 times x2, right? And how you would compute the values in a single in a particular hidden layer, right? And so in matrix notation, which we you would you can simplify it to this formulation, right? And also that, and then you have your activation function, which like could be a sigmoid or a ReLU or a tanh, right? So you apply the activation function element wise, right? So this was a key point, right? You need these activation functions, otherwise it's, so without this, right, it's just a linear transform, right, where you're just combining the different weights, like the different matrices W1 and W2. So this is oops, what's that?
Hey, so Mehul, while you're trying to get rid of that blue stuff from your screen, I've got a question for you. So if you go back, just around the just there, right? So let's say our problem was say sentiment analysis, or right, like classification. Is this a good or bad? That would be your last layer, right? Now, now if your if you look at the X1 and X2 and so on. Those are all of the words that would allow you to determine whether your sentiment analysis is good or bad, for example. But are you saying then that then surely your inputs has to be the entire corpus, right, for you to be able to determine some sentiment? But that's huge. So what is your input X1, X2, and so on?
No, the input is the word embeddings, just like we said before. They are derived from the corpus, right? So you don't need the entire corpus as the input. You just need the embedding vectors for those words that are in your movie review or whatever you're looking at.
Okay, so maybe I'm using the wrong terminology. When I say corpus, I mean like all of the words that you have
in a document,
right?
So
in a document.
What it means is that it is a 1,000-word paragraph, then there will be 1,000 inputs. That's what you mean, right?
Yeah, if you're doing movie reviews, for example, the X's are all the words in the movie review. But they're not all the words in the whole corpus of movie reviews.
Right, okay. Yeah, I think I was using the words incorrectly. Thank you for clarifying that. Yeah.
Okay.
It's still very large. So your point is.
Yeah, I know. It is you. Yeah. Okay. Yeah. Okay.
Mm-hmm. Yeah. So these non-linearities are key. I have okay. Maybe I'm running out of time. I have an example where what I did is I just used. I had the MNIST dataset, right? So I just used a logistic regression classifier, and I'm not sure why this blue stuff is coming. I'm not even moving my mouse. Anyone know? Okay. So I had a simple example where I just took the MNIST dataset. I have a logistic regression classifier, and I have a simple one hidden layer, like just a one hidden layer neural network. And I run it on the same training data. And with this, and you can already see like a difference in performance with just like say a few epochs. Maybe I'll because I'm running out of time, I was going to show you like the difference in so I basically just built a neural network and with just one hidden layer. And what I wanted to do here was I just want to compare, okay, like a simple logistic regression with a one layer hidden neural network, and what's the difference in performance. I'll post the links to this. So here with, it quickly went up to 90 something with this one layer neural network. And with the logistic regression one, I was around I was around 85, yeah, around that, yeah, 85, right, 85 for, and in here I did some things like it's part of a tutorial I had done a few months ago. You basically write the logistic regression and the neural network on your own to go through it. But sorry, I didn't. Yeah. I can share these links. So this is basically what this is just a platform to share my Python notebooks. So I can share it with and these are public, and I will share it in the chat window.
Can you put it on the Slack channel?
Okay. Yeah. Sure.
Great. Yeah.
Yeah.
Thank you.
Yeah, it's great because you can it's part of this. It was a part of a series which was quite nice. So if you have time, I like, and if you're interested in PyTorch, they went from regression. So this series went through regression, logistic regression, and then a neural network. And yeah, so that was quite nice.
So this is any course or something?
It's on YouTube. Yeah, I'll put the link in Slack.
Please, yes, thanks.
Okay, so here, okay, so so we talked about traditional machine learning, neural networks, and a side note. I think this is what this makes the lecture a little hard is you have both the neural network stuff and like NLP related stuff stuffed into one lecture, right? Because in the CS229, and the neural networks is just one lecture by itself, right? So here so he talks about this named entity recognition task. So here you have like, you want to find things and also classify names in text. So for example, is United States mentioned, right? Or is France mentioned? So these could be in the classification task. These are locations, right? And then European Commission is an organization, and so on. And he gives a lot of I thought this was very interesting. Like there are a lot of industry applications, right? You want to you have documents and you want to say how many times Facebook is mentioned in that document, or how many times is your company being mentioned, or maybe he gives a bunch of different examples for classifying words in a text, right? So he calls it named entity recognition. And then now, like we said before, you have the words, so you could classify words, and he says there are some problems about it, and he talks about this he mentions in the lecture, he mentions BIO encoding, but he doesn't describe it. He doesn't dive into the details of BIO encoding. So I didn't know.
That's
BIO.
just beginning inside and outside. So like foreign ministry is one word, right? You want that whole thing to be categorized.
Right. Okay.
So that's how BIO encoding is.
Okay. Thanks. I see. Okay. Yeah, and then he talks about this named entity recognition is hard. So for example, in this example, you have something called a First National Bank. So is it National Bank, or is the name of the bank First National Bank, right? And another thing that another example he gave is Future School, right? So is the name of the school Future School, or is it a school in the future, right? And he gives this example about Charles Schwab, like in so it depends on your context. So many in Charles Schwab.
Good, Nick. How are you?
Oh,
somebody needs to mute themselves, I think.
Yeah. Yeah. So except so the context matters. So here in this sentence, when Larry Ellison and Charles Schwab can live discreetly among their wooded estates. So here we are referring to the person, but in many other documents, like you would, when you first think of Charles Schwab, it's it's a firm, right? You think of it as a
Okay, so named embeddings and what we would just look at, the thing's gone out of my head. The ones with the nodes and the connections.
The neural networks, or
the neural networks,
neural networks. Imagine that we're talking neural, and that's okay. So with that, right? So if for example if the purpose of the named embeddings was to have your output as the classification as in person or organization, is that so? Let's say there were three classes, right? So person, organization, and other as your final layer, right? Are you saying your inputs would be all of the words in this thing, so the European Commission and so on? Is that what we're saying? Because that doesn't make sense to me. Because
the words are the words are the inputs in some document, right? So you want to classify this document. You want to pull out all the named entities, right? So the input is a document which might have thousands of words in it, and the output, if you go back to the neural network, is the classes, and each named embedding would be a class, right? Yeah, the A1 and A2. Yeah, the output of the final layer is the different named entity classes, like org for organization, PER for person, MISC for miscellaneous.
Okay, so if it doesn't actually, because if my input is all the words in that paragraph, right? So X1 to Xn are all the words in that paragraph, and my outputs are one of those three classes, how am I differentiating between them, right? How am I learning when they're all my input?
So I'm not sure how Chris Manning does it in this lecture, but usually for NER, we have an architecture called seek to seek. So it's sequence to sequence. So your input is a sequence of words, and each word in the input sequence has a corresponding output. So yeah, that's why it's called a seek to seek. So if the first word is a org, then it would have a org output. If the second one is a person, it would have a second. The second output in the output sequence would be a person. It goes on like that. So the output is also a sequence. The input is also a sequence.
Yeah. So that would be a recurrent neural network approach, and the other approach is similar to images. You think of your say a document or a paragraph as a one-dimensional array, and you do a convolutional network type approach on it. Generally, with that approach, the array size is limited. So you could have, let's say, you 300 words. If your paragraph has less, then you pad it. If it is more, then you have to clip it. You have to make some choices there. But otherwise, it almost like image processing with neural networks.
I think it was Gautam who said the answer is that you're tagging each word. It's a seek-to-seek model, and you're tagging each word with a tag that classifies it as as some named entity or not, right?
So then your output isn't.
Yeah, you're right. You're right. Actually, John, that it doesn't make sense to look at this particular thing we're looking at here. That isn't what the output would look like, and Gautam said that it should be someone said that it should be a sequence-to-sequence model, so that you have the same number of outputs as you have inputs. And the analogous problem in image processing is object recognition, where you have to label each pixel as to what class it is, whether it's a bicycle or a pedestrian or a street. It's a similar kind of problem.
Later, just in the next few slides, he goes over a simple model, simpler than the two that have been mentioned, and obviously, therefore, from an earlier time of how to do the named entity recognition within a context. So it's just there in the next several slides. But it's a simpler model than what Gautam and talked about.
Okay, I guess the question I have is, we've been talking about neural networks for up to this point, but neural networks don't make any sense in terms of us finding a solution for named embeddings.
It will, if you look at
named entity recognition.
They will, if you just hold on, they will in Channing's lecture, as well as in the way that, and in the longer run over multiple lectures, neural networks will be the best at solving that problem. So you see that
as Murat said, you get these tags, you get these embedding tags by using RNNs, which are basically series of neural networks like the ones we're looking at. the seek-to-seek model is basically a series of neural networks, just like the ones we're studying.
Okay, I should wait because I did listen to the entire lecture.
But you're absolutely right that the diagrams that we've been looking at don't make sense for the generalized problem of tagging words with named entities. But then, as Srinivas pointed out, you can do something like take the documents in the vector in the input and average them. Take the words in the input sentence maybe and average them, and then classify it as one of the other of the named entities. So you could classify each sentence saying this sentence is mostly about mostly about persons, or this sentence is mostly about organizations, or paragraph. You can do it with a paragraph. So you could actually do something that corresponds to these neural networks, exactly the ones we've been studying, basically making it a classification problem, and the outputs are the average embedding tag for that paragraph, if that makes sense.
Okay. Yeah. Yeah. Okay. Great. Thank you. I appreciate your input.
Yeah. I'll just like the hard part about this lecture is like if you see the way it's broken up. So like it's like we had a classification review, then a neural networks introduction, and then where we it's like the named entity recognition, right? And the next is there is some like maybe like Srinivas said, it's an older from an earlier time, right? Like how to do like this word window classification, right? So that's the next section, and
that's also in a way it's just tagging words, therefore solving the named entity recognition problem. In fact, from what he said, and if you look at it, it recently won awards for the paper that he refers to won an award for its impact over a decade, which is a significant time in neural networks these days.
And so this is where I was struggling too when I went through this. It's like you have you have the neural networks, right? And then I want to you have the matrix calculation introduction, because this is key, right, to the next part, which is back propagation. So since I have 7 minutes left, how should I do this? Should I just introduce the matrix?
My suggestion is finish the NER stuff and the binary stuff so that you can combine the matrix calculus introduction and the rest of the next lecture, which is all about matrices, and make that a single thing which is focused on matrices. Don't switch back and forth.
That makes sense.
Okay.
Go for 4 and 5. Yeah.
Okay. Thanks. Okay. So we were at right. So this here he explained like why NER might be hard, and yeah, then you get this intuition to binary word window classification, right? So because the context is important, right? So like for example, the two examples he gives is to sanction could mean either to permit or to punish, right? And like to seed is either to place seeds on the ground or to remove seeds from a watermelon, right? That was the two examples which I thought of. Yeah, that's interesting. And then other examples is Hathaway. So Berkshire Hathaway is a big company, and Anne Hathaway is a Hollywood star, and same as you could have Paris, France, or Paris Hilton, and so on. Yeah, so here the main intuition is you're looking at the neighboring words, right? So and the idea is like the simplest way to do it would be to average the word vectors in a window, and then classify that average vector, but then you would lose where you were in the text. So in this case, you have so the example we start with is museums in Paris are amazing, right? and our window length is 2. So it's Paris is the center word, and you have two words on each side, right? So you have your vector is is your x, you have this window right here, right? Okay. And now is yeah. So we want to so given that window, what is the probability that that we belong to a particular class Y, right? So here this is your predicted output probability from your model, right? And if you remember the cross entropy equation from before, you know the ground truth, right? You have that okay, Paris is a location, so you can now you can use cross entropy to compute compute this term, right? Yeah, and this is the paper that this is the paper that won the time test of time award, right? So we so we basically want to classify we want to classify whether this center word is a location or not, right? And here what we want to do is only so we are now in the supervised learning context, right? So only some positions should get a high score, right? So this is basically if that word is a location, so you don't want a high score for in or R, right? I didn't follow this this corrupt windows part. If anybody has
yeah, the same as negative sampling, which I think was mentioned in the previous lectures. Bottom line is you want to increase the probability of the correct things being named as location. So for example, in this case, Paris, and then you'll take a bunch of examples which are negative, which means that they are not locations, and you train in order to increase the probability of the correct thing being tagged and the incorrect things not being tagged. And as you go through and learn that and run that repeatedly, then you'd increase the probability of you finding the correct named entities in documents.
In both these examples, you're mainly focusing on the center word.
Yes, just like word2vec. That's why the comparison is very apt, because even in word2vec, you do the same thing in negative sampling, because the softmax, the bottom line is the denominator of the softmax is too big to go through. It's the entire vocab otherwise. And here you'll just use some limited number of samples, negative samples, to do that, wrong examples.
So you can do this negative sampling to build your, because I was wondering how you would build your training set, right? Like for
I believe in one of the homeworks you actually do, maybe the next one, but essentially it's just sampling, random,
okay,
but negative.
This is so you want like we said, we want if it is a location, you want a higher score, right? So in this case you have you have one hidden layer where and he talks about this intuition that the main idea to add this hidden layer is to capture nonlinear interactions between the input words. Yeah, and like so. Yeah, if so for the one example that you see is only if museums is the first vector, should it matter that like that the second vector is that in is in the second position, right? So so for example, the other negative, all museums are not in Paris. All museums. So you could learn. So you add this hidden layer to learn these nonlinear interactions, and the rest is similar to what we said. So for example, you start with your I think going through the sizes is important. So X is in a dimension in the space where is a 20 cross 1, and then you have because your weight matrix is 8 cross 20, and then finally you have a single score, right? You get a single score for each for each window. So you can compute a score for each window. That's just
excuse me, I just wanted to say something. If you wanted to go to Darren's meeting, the next meeting, the projects meeting, it's already started. So we probably should conclude this one.
Okay. Okay, I can stop here. Yeah, because other people might want to go to the next one.
Thank you very much.
Sorry. Yeah, sorry, I was sorry I didn't get through all of it. I'll try to summarize the matrix math and the backpropagation in the next